Hello and welcome back to California Geology. I'm going to continue on with the coast ranges today and begin with the salinian block. So one thing about the salinian block, if we look at the map of California or the geologic map of California, one thing I want you to compare here are the red rocks. The red rocks here are the Mesozoic granitic rocks of the Sierra Nevada. So you can zoom in a little bit here. So we got Mesozoic granitic rocks up here in the Sierra Nevada. And you can see there's a variety of them also exposed here in the coast ranges, right? So the prominent ones, there's actually one up here at Bodega Bay, Bodega Head. Then there's the Point Reyes Peninsula, which is up over here. And then there's Montera Mountain, it has an exposure. And then there's the Santa Cruz Mountains. Here at UC Santa Cruz, there's some granite exposed there locally. And then the Gavilan Range all the way down toward the Pinnacles, which are in the south over here. And then on our field trip, we'll see the Santa Lucia Granodiorite, which is over here in Carmel and Monterey. And you can see there's some little isolated features there. And then there's some granite exposed down here near San Luis Obispo. And then we'll see as we get to the Tehachapi range down here in the San Emigdio Hills, these are all part of the Sierra Nevada granitic batholith. So we also see Mesozoic rocks, but also note that the Mesozoic rocks, or these granitic rocks, occur on the west side of the San Andreas Fault. And then these brown rocks you see right in here, those brown rocks are the metamorphic roof pendants. And so that's a SIR series. Remember, the Mesozoic granites intruded these older Mesozoic to Paleozoic sedimentary rocks and metamorphose them via the contact metamorphism. So that's a Hornfels facies, high grade, low pressure. And so these are the metamorphic. So there's marbles, there's quartzites up here, schists, even some gneisses up here in these metamorphic roof pendants. There's also some exposed here at UC Santa Cruz, which we'll see on Saturday during our field trip. All right, so how do we get these Sierra Nevada granitic rocks plus associated roof pendants in the coast ranges? Well, it has to deal with the San Andreas Fault. And one thing about the San Andreas Fault is if you were here in the Gavilan Range and you're facing the San Andreas Fault, to get to where the Sierra Nevada granites are exposed along the fault, you would have to step far to the right. And that's called a right lateral transform, right? It's because you're stepping to the right. Or if you're here at the Tehachapi Range in the Sierra Nevada granites, you face the fault and you would have to step again to the right to get to where these granites are in the coast ranges. So the San Andreas Fault is an example of a right lateral strike slip fault. Now, so we talked about the granitic rocks. So another group of rocks that occurs in these are the roof pendants. So remember, these are the metamorphic roof pendants. They were metamorphosed at relatively high grade and similar to the rocks in the Sierra Nevada, the High Sierra. Now, remember, Mesozoic California was a subduction zone. So the Mesozoic granites of the coast ranges formed during the same Mesozoic arc as the Sierra Nevada. So remember, there's going to be the hydrous flux melting with the ascending magmas here, and then the batholith is forming in here, right? So that would be the batholith, Sierra and batholith. And so those coast range Mesozoic granites are also going to be exposed or also formed in the same fashion, except that they were truncated by the San Andreas Fault in the past. So the magmatic arc and the salinian block represent a continental, so the basement of the salinian block represents a continental magmatic arc. So how could these be exposed out here in the middle of a Mesozoic subduction zone? And of course, is the San Andreas transform fault. And so I've showed you this figure before, where we have the eastern block of the Franciscan and the western block, and sandwiched in between here is the salinian block. And the key thing, it's exotic. It came from someplace else, or at least it originated probably down here in Southern California, or maybe even farther to the south, and has been tectonically transported and then placed into its current position. So So the answer to moving this Sierra Nevada type granitic roof pendants, rocks and roof pendants, is really through this San Andreas fault. And remember, we said it's a right lateral sense of motion. And there's been at least 315 kilometers, or about 180 miles of displacement northward. So the salinian block is probably splintered, internally fragmented, and the block may be really stretched out as it was being slid along the San Andreas fault, kind of rotated blocks, so a variety of structures going on there, kind of distended is the word I'm looking for. Now, let's define the salinian block, just to kind of get a good definition here. So the salinian block is an area in the coast ranges underlain by granitic and high-grade metamorphic rocks. So the granitic rock are the salinian granites, the high-grade metamorphic rock are the roof pendants. And so it is bound on the east by the San Andreas fault, on the west by the Sur Nacimiento fault zone. So down there in the Santa Lucia range. The basement of the salinian block, which represents a continental magmatic arc, contrasts sharply with those of the Franciscan Formation that lies both east and west. Remember the eastern block and the western block. So remember the Franciscan is an oceanic beast, right? Whereas the salinian block is continental. So right away there's a fundamental difference there. Also the Franciscan was metamorphosed at high pressure and low temperature, which in contrast, for the Sur series, one thing we should point out for the Sur series, which are the roof pendants, these were at high temperature or high grade and low pressure. So basically complete opposite. So now these two rocks are next to each other. So that's how it kind of was a puzzlement to geologists before we figured out plate tectonics. It was really hard to interpret this geology. How can you have two very different rocks that formed in very contrasted, very different environments together? And well, now we can explain it through transform faulting along the San Andreas fault. So this salinian block, the rocks of the salinian block originated in an area of the present Mojave Desert region between the southern Sierra Nevada and the Peninsula Ranges batholiths. And they have been displaced at least 315 kilometers northward by movement on the San Andreas fault. So if we look at our map one more time here, note that down here in Southern California, if it wasn't for this kind of empty area in the Mojave, the Sierra Nevada arc would extend and connect down here with the Peninsula Ranges down here, which actually go through the spine of Baja California here, at least through northern Baja. And so it seems like the granitic rocks in the coast ranges here were in this region here and got kind of broken up and transported northward along the San Andreas fault. Now, what's the evidence for that? And so the evidence here, it really brings us to our fourth and fifth groups of rocks, right? So those include the Cenozoic volcanic rocks and the Cenozoic sedimentary rocks, right? So when we look at Eocene, 50 to 40 million year old sedimentary rocks, Eocene and Oligocene, we find that they have been offset. They have been cut by the San Andreas fault, and they do show separation by about 315 kilometers, right? And in fact, before we do the Pinnacles, if we look at there's a couple of formations down here in Southern California, one called the Mint Canyon Formation, and the other one called the Caliente Formation. So here's this is Southern California. LA is here. Here's the San Andreas Fault. Caliente Formation here. Mint Canyon Formation here. And then if we go down here, I want you to look at these Chocolate Mountains, which are over by Joshua Tree. And these these mountains here, these Chocolate Mountains, they're volcanic rocks, and there was erosion which brought material into sedimentary basins to the west. But then movement on the San Andreas Fault has taken those rocks and moved them northward. So Mint Canyon and Caliente. Both these formations are about 13 million years old. In fact, the Caliente is famous for having Miocene horses, so ancient Equus fossils. And so quite a number of fossils in these rocks, so they're terrestrial. And so, and they're separated by about 260 kilometers, right? A little bit younger, 13 million years, right? So if you go back to 28 million years, when the fault first started developing, then you can get a good measurement of the true distance moved. So now let's look at the pinnacles. So the pinnacles are going to be the next group or the next line of evidence here. That's going to tell us that there's been at least 315 kilometers of displacement. And so one thing that we know about the Pinnacles and Enoch volcanics are both about 23 million years old. So, which means that this 315 is a minimum distance. So, because the fault had been moving already for 5 million years. Remember, it started at 28 million years. So these two fields represent one former volcanic field that was split apart and offset by the San Andreas transform fault. In fact, I have a little diagram here I want to share with you. And well, in fact, we'll look at the map first. And so this is actually from your textbook. And so down here in Southern California, note that this Enoch volcanic field is east of the San Andreas fault. So this dark line right here is the San Andreas fault. Remember, there's movement going like this. So we'll show some half arrows like that. So where the Pacific plate is moving north, the North American plate is moving south here. So, and note that the Pinnacles up here are on the west side of the San Andreas fault. So, in fact, these two volcanic fields were right next to each other. In fact, it really was part of the same series of volcanoes. So there's probably 2 or 3 volcanoes in this region, except for the Pinnacles part of it has been moved northward. And then there was a paper here done, in fact, we can look at the paper, by Vincent Matthews, a UC Santa Cruz geologist back in 1973, who first started looking at it, and he looked at the Pinnacles-Enoch correlation, and he was looking at rocks in Southern California again, down in this Enoch field, and could relate them to the Pinnacles field. And what he found, in fact, we'll look at his diagram, which occurs in your textbook in Hardin, this one here. He found that in the Enoch volcanic field down here, he had a granitic basement, and he also found that same granitic basement over at Pinnacles. So here's the Pinnacles and here's Enoch. And then he found that there was this glassy lapilli tuff. So it's a pyroclastic unit composed of lapilli-sized fragments, and he finds them in the same position both at Pinnacles and at Enoch. Then they had a pretty massive flow-banded rhyolite section here. And this flow-banded rhyolite occurs both at the Pinnacles and at Enoch. And then there's this, at the top of it, there's this perlite. Perlite's like obsidian, and so it's very glassy again, but it's been hydrated. It's older. Usually obsidian devitrifies, so it doesn't really last more than about 5 million years. So this one being 23, so it's been altered. But it represents some obsidian here, and you find it both at Pinnacles and at Enoch. So needless to say, you have the exact same stratigraphic order, both at Enoch and at Pinnacles. The only thing you're missing at Pinnacles, you're missing the high peaks formations, which is this rhyolite breccia. This is what rock climbers like to climb on at the Pinnacles. And it's probably because when the Pinnacles were moved northward along the San Andreas Fault, they were probably buried by marine sediment and not subjected to erosion, whereas the Enochs were probably exposed for that duration, 23 million years, and they did experience erosion, and this unit from Southern California was eroded away. But anyhow, the similarities are the stratigraphy, the order of rocks are identical, and what's more, both of them are 23 million years. And there's even here's this AGI unit, which is a volcanic conglomerate. So you see it here at Pinnacles and here at Enoch. Well, that volcanic unit, a volcanic conglomerate, has fossils in it of marine plankton, and the plankton are identical. They're both the same age. So again, indicating that this is the same volcanic field, but split by the San Andreas Fault and transported 315 kilometers to the north.